Okay, hello everyone. Back down in the workshop, and I just wanted to do a video for Stephen to just demonstrate something that may help to calm a few nerves. If you look here on the bench, what I have is I have a 240 volt to 12 volt step down transformer powering a load. You don't need to come in real close, you need to be watching the screen, yeah? Powering a load that's coming through a rectifier. The transformer itself, the transformer core, has atop of it the internals of a microwave oven transformer, some steel laminations, and on those steel laminations is the coil from a solenoid. It's standing off about 2 inches probably from the transformer coil that is live. And then underneath the transformer coil under the table there's 3 magnets, and on top there's another 3. So those form a magnetic circle. Now, the output of the coil, the output of the induction coil that is on the core of the microwave oven transformers is what we're interested in. I have the oscilloscope turned on and hooked up. If I hook it to the output of the induction coil, we can see on the scope the trace is rather small. It's set to times 10 and 1 volts on the voltage scale. So it's quite a small voltage. It's only about 10 volts there. So it's just on 10, and it's quite a broken up and long signature. The cycle on the milliseconds is at 5 milliseconds per graticule, so it's 1 to 5 graticoules per millisecond, per 5, sorry. Right, come back out. Now, what I wanted to demonstrate was what happens when I place myself in circuit on the scope. If I place myself in the circuit of this induction, what happens on the scope is we get that trace on the scope. Have a look. So I'll disconnect myself, and that's just one side of the scope connected to the circuit. If I connect myself in, we can see that the trace goes back to where it was. So without me connected, one side of the scope trace, just the one input signal from the scope, I don't know whether that's coming in really nice, you need to not move so jittery. Just one of the leads of the scope trace is hooked to the induction coil, and that's the signal. If I place myself in there, the signal drops back to what it was when it's connected. Come back out. Now, what I wanted to demonstrate was these placing a condenser in series with the coil, in parallel with the coil. If I place a condenser on there, that's to one, and that's to the other. Sorry, this is not a condenser, this is a capacitor. The scope trace drops to 0, and if I increase the frequency, come back down to 1, lower the voltage, you can see that there's minuscule voltage. That's now at 50 millivolts per graticule. We'll come back out to 1 there, and we can see that there's virtually nothing with this. Now I'll reverse the polarity just to be sure. the scope. Still nothing. It's the same. However, if I take that off, that one there, and basically, you got that in shot? losing light, aren't we? Basically throw that to the bin and use one of these, which is a little rectangular one, which is, when you pull it apart, a lot more like a condenser than a capacitor. Oh, fiddly. Let's see what we get on the scope. So we can see that there's now a collection of energy that wasn't there before with that capacitor. And you can see that it's resonating energy. I'll zoom in. That's now 0.5 per gradical. And although it's all hashy, it's quite there. Now I'll touch across the two and nothing happens. I'm connecting myself in parallel and nothing happens to the trace. No short, no change, no nothing. Now, if I use a bigger one, this one here, which is a microwave oven capacitor, that's one side there. Is that right? Yeah, that's right. And that's the other side there. Have a look at the voltage now. Can we see that on the scope okay? On the camera? I can't see the screen. Yeah. So now we have somewhere on the range of 1, 2, 3, almost 30 volts. Well, no, it would be 30 volts if I bring that right down. So I'd say 30 volts because the scope trace, the probe is on times 10. 8 times 10.5 on the scale. If I go to 0.1, if I go to 1, it's 1.3. So it's 13 volts or thereabouts of energy coming from this induction coil with this capacitor or this condenser. If I now go across to a motor run condenser, we'll have a look at the voltage from there. And watch what happens to the scope trace. A lot tidier. It's at 1 volt per gradical. It's 11 volts. And that motor run condenser actually makes it spark. Now, that's not the most interesting part. The most interesting part is this. The most interesting part is if I take an amperage reading on the input of the coil. Where did my clamp meter go? Up there. Go and grab the clamp meter. I've got this. What is it? No, just up there on the shelf. The first shelf, yep. Careful of the leads, they're all wrapped up, I think. Torrance put it up there. Yep. Okay, I got it. So, if I take an amperage reading of the input on the AC primary side of the transformer with the load attached, I might have to, no, there we go, 0.1. It kind of flickers between 0 and 0.1. I'll go another wrap, I'll put another wrap around the pickup coil, Try not to zap myself because that's live. There we go, steady 0.1 amps. Can you read that? Is it reading? It is? I can't see it. Cool. So that's a steady 0.1 amps. Now, if I disconnect this load down here, can you come across and see the load? That's the load on the secondary. 18 volts coming to a 24 volt light globe. If I disconnect that load, watch the meter. Can you see the load as well? Yep. Right, I'll disconnect the load. We can see now that there's no current draw on the primary. What's happened to the voltage on the scope? We now have, instead of the 11 volts, we now have 122 volts. So it's doubled the voltage by removing the load on the primary. So that's basically energy for nothing, simply by magnetic induction going into this coil. Now, great. The other thing I wanted to demonstrate, what time are we at? 11 minutes. No, that's it. That'll do. Alright, that's all.